Welcome back, Science Fam. This is part 2 of worksheet number 1 for one-step mole problems. We are currently on number 8. If you take a look at what we start with, we have 750 moles of H2O2. That's hydrogen peroxide. Since we're in moles, we're starting at mole island, and it wants us to go to liters. So this hydrogen peroxide is actually a gas. According to this, a gas at standard temperature and pressure. We're going to liters. If you remember, volume is measured in liters. So we're going to be headed to this island. To go from moles to volume, we're going to need to take that bridge on the left, which means we're going to use this conversion factor. All right, so let's write out what we have to start with. We have 750 moles of hydrogen peroxide. I'm then going to hit a multiplication sign and put a line because that line is going to tell me that I need to use my conversion factor. According to that, on top it says to put 22.4 liters, and that's of H2O2. And then at the bottom, it says to put 1 mole. So that's what I'm going to do, 1 mole of H2O2. Now that I have that, let's make sure that our units cancel out. Remember, this is like being in a fraction over 1, so this is in the numerator, moles of H2O2. This is in the denominator. Those are going to cancel out because numerator and denominator divide each other out, right? That's just basic math rules. So now that we have that, the only thing left are the units of liters of hydrogen peroxide, H2O2. Is that what we were looking for? Yes. So we're good with the units. Now we just have to do the math. Remember, you take the first number, multiply by the top, divide by the bottom. So that would be 750 times 22.4 divided by 1. Throw that in your calculator. What you end up getting is about 16,800 liters of H2O2, if that was hydrogen peroxide, a gas at STP. To be completely honest with you, I don't believe hydrogen peroxide actually is a gas at STP, so that is a little bit of an error in the worksheet, but we'll follow along with the rules for the map for the sake of learning how to do the map, but I believe that is slightly off. But all good. So we're going to move to number 9. We have 5,944 liters of this boron trifluoride. So we're in liters. Remember, liters then means we're going to start at volume island. It wants us to convert to moles. So I'm going to convert back to moles. So this is actually the opposite of the last problem. You're going to go from volume to moles, so you're going to use the bridge on the right, which means you're going to use this conversion factor. So to do that, let's write down what we're given and starting with. So we're given 5,944 liters of BF3. We then want to multiply and draw the line to use this conversion factor, which tells us to put 1 mole on top for every 22.4 liters on the bottom. Now notice I'm going to put BF3 on top and bottom because that is the compound we are currently talking about. Now that I have that, let me make sure that my units cancel out. I've got liters of BF3 in the numerator and the denominator, so those cancel out. So I'm left with units of moles of BF3. So the map really does help you figure out what to multiply and divide by. So because we're going to take the first number, multiply it by the top, divide it by the bottom, that's going to be 5,944 times 1 divided by the bottom number, 22.4. And when you do that, put in your calculator, you end up getting about 265.36 moles of boron trifluoride. So there you go. We converted again from the volume, how much space it takes up, all the way to moles. All right. And we know once we get to moles, could you then convert it like to mass or particles? Absolutely. That's where we're headed next after our one-step problems. But let's stick with learning the map and getting 1 steps down. Let's move to number 10. For number 10, we have 5.6 moles of tin 4 chloride. All right. According to this, it says it's a gas at STP. Again, unfortunately, I think that's an ionic compound that normally wouldn't be a gas. My apologies, there's some errors on this worksheet, but for now we're going to assume that it is a gas at STP. But that starts in moles. Notice that the units are in moles, so that's what we start with. A lot of people think, oh, it says gas at STP. I must have to go to this one. No, not necessarily. We're starting in moles right here. It's just letting you know that it's a gas according to this worksheet. But anyways, it wants you to convert to liters. and liters is volume. So that means you're going to start with moles and convert it to volume, which means you're going to use this conversion factor. So if we look at number 10, we started with 5.6 moles of a substance. So you always write down what you're given to start, and then use the conversion factor from the map. It says to put 22.4 liters on top and to put 1 mole on the bottom. 1 mole on the bottom. That's 1. Okay, I know that it's tin 4 chloride, so I'm going to carry my compounds. You might be asking too, why do you keep carrying the compound? It seems like a waste of time. But when we start doing multiple step problems and converting to other things, it's actually going to be important for you to keep your organization. So these are good habits to start now so that they can lead to more success later. Anyways, top and bottom moles of tin 4 chloride cancel out. I'm left with units of liters of tin 4 chloride. If I take a look, double check, did I want liters? Yes, so I'm good. My units are good. Now I'm going to take the first number I start with, multiply by the top, divide by the bottom. So that's going to be 5.6 times 22.4 divided by 1. And when I do that and throw that into my calculator, what I end up getting, 5.6 times 22.4, is 125.44 liters of tin 4 chloride. There we go. We got our answer for that using our mole map. Let's move on to number 11. Number 11 is going to start with 26.5 moles of calcium carbonate, and it wants you to convert it to grams. So if we're starting in moles and it wants us to convert to grams, that means we're going to go to mass island. To go to mass island, we're going to need to use the conversion factor, molar mass over 1 mole. Just a reminder, molar mass, remember you get that off of your periodic table. So it's just the mass of the compound. So let's rock it. Okay, to start with, we're going to write down what we're given. So 26.5 moles of calcium carbonate, CaCO3. I'm going to multiply and draw my line. I'm going to use my mole map. It says to put 1 mole on the bottom, 1 mole of CaCO3. And on top is the molar mass. I have to use my periodic table for that. So I've got to add up calcium, 1 carbon, and 3 oxygen. So if you go on the periodic table and add all of those up, what you should get around is about 100.09 grams of calcium carbonate for every 1 mole of it. Remember, when you have 1 mole of a substance, it turns the periodic table's AMU's mass into grams. Let's double check to make sure our work makes sense. Moles on top and bottom cancel out. I'm left with grams on top of calcium carbonate. If I look at my original problem, it wants me to get grams, so it looks like my work is good. I'm going to start by taking my number I have, multiplying by the top, dividing by the bottom number, which is really just 26.5 times that molar mass, 100.09, divided by 1. Once I throw that in my calculator, I end up getting a fairly decent sized number, 2,652.39 grams of calcium carbonate. So I converted my moles all the way over to mass, and I got my answer. Let's move on to 12. We have for 12, 2,500 molecules of oxygen. Notice it says a gas at STP, which normally associates with volume, but in this case it doesn't matter because you have molecules, and molecules is found under particles. So we're going to start a particle island, and it says to convert to moles. So I'm going to use that top bridge over to mole island, which means I'm going to use this conversion factor. Now that I have that, let me write out what I'm given. I'm given 2,500 molecules, so I'm going to put MC for short, of oxygen. And then, after I wrote down the number I'm given, I'm going to use my conversion factor. It says to put 1 mole on top and 6.02 times 10 to the 23rd on the bottom. Notice it says particles on the bottom. Let's be specific. We're talking about molecules. So MC for short for molecules, and we're going to put O2 on both of them to keep everything labeled properly. Let's double check to make sure our units are canceling. Molecules of oxygen on the numerator and denominator cancel out, so you're left in units of moles of oxygen. Moles is what you're solving for, So it looks like this answer will be in the proper units. To actually do this problem, remember we take the number in the calculator, multiply by the top, and divide by the bottom number. Please remember to put 6.02 times 10 to the 23rd into your calculator properly. If you don't know how to use it in scientific notation, remember most symbols is EE for scientific notation. Make sure you are using your calculator right and double check with the answer. If you're off by one exponent, it means you're throwing in a multiplication sign in the wrong place or somewhere. In fact, when you put in 6.02 times 10 to the 23rd in most calculators, you actually don't use the multiplication sign or the 10. You usually use 6.02 and then an E button and then 23. Again, that is up to you. Make sure you know how to use that actual calculator, or else it could really, work against you. So let's take 2,500. We're going to multiply by the top, which is 1, and divide by the bottom, which is 6.02 times 10 to the 23rd. This is division, by the way, over here. We're dividing. All right, now that we've done 2,500 times 1 divided by 6.02 times 10 to the 23rd, you end up with 4.51 times 10 to the negative 21st. So it's a really, really small number. Why? Because if it's 4.51 to the negative 21st, you would move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 21 places backwards. So it'd be 0.00000000000, 20 zeros, and then 451. So a very small number. But anyways, this is a very small amount of moles, but that makes sense. You only had 2,500 molecules of oxygen. And remember, a molecule of oxygen is incredibly small. So it makes sense that there isn't that many moles of it. All right, let's move on to number 13. Lucky 13 says there is 22.4 liters of bromine gas, and that's at STP. So that means we're going to start at volume, because remember, volume is in liters. We then want to convert that to moles. So moles are right here. So if I'm going to go from volume to moles, I'm going to use the right-hand side bridge, which means I'm going to use this conversion factor. So let me write it down. 22.4 liters of bromine. And I'm going to multiply and draw the line and use my conversion factor. It says 1 mole on top, 22.4 liters on the bottom. And I'm going to carry across my object, which is bromine molecule. All right, now that I have that, let me double check that my units cancel out. Liters on top and bottom cancel. I'm left with moles of bromine, which is what I'm trying to solve for. So excellent. I know that my units will be correct. Let me just do my math. Take the number we start with, multiply by the top, divide by the bottom. So that's going to be 22.4 times 1 divided by 22.4. And look at that. That ends up being 1. So your answer is 1 mole of bromine. And that makes sense. If you have 22.4 liters of bromine, there's 22.4 liters of bromine for every 1 mole. So it makes sense that you have 1 mole of it. Awesome. Let's take a look at that and move on to number 14. We have 22.4 moles of bromine to start for number 14. So we're going to start at Mole Island. We want to convert that to liters. We know liters is the amount of space something takes up, so we're going to Volume Island. To go from moles to liters, we're going to have to use our conversion factor on the left-hand side. So I'm going to start with 22.4 moles. And at first, some of you might think, whoa, are we going to end up with 1 again? This is very similar to the last problem. But nope. Since we're going from moles to volume, 22.4 liters is going to be up on top, and 1 mole is going to be on the bottom. So actually, if I carry my bromine across, let me double check to make sure my units are canceling. Moles of bromine, top and bottom cancel, so I'm left with liters. Liters is what I'm looking for. So liters of bromine is what it is. I could have just wrote the L. I don't know why I wrote liters out all the way. The shorthand form would have been easier, but too late. So I'm going to take my number I start with, multiply by the top, and divide by the bottom. So when I do that, that's really going to be 22.4 times 22.4 divided by 1. When I put that in my calculator, 22.4 squared is 501.76 liters. So when you have 22 moles of bromine, it takes up 500 liters of space. That's like 250 bottles, 2-liter bottles of like soda. You buy those bigger bottles, if you think about it. So that takes up quite a bit of space. That's quite a bit of volume. But we use the mole map to do number 14. Let's move on to number 15. Taking a look at number 15, we've got 500 formula units of sodium chloride. You know, you're thinking, wait, what are formula units? What is that? But it says it right here, guys, on the map. Formula units is in the particle island. So you're going to start at particle island and convert to moles, which means you're going to use the bridge on top, which means we're going to use this conversion factor on top. So I'm going to start with 500 formula units. The shorthand form for that is FU. Yes, you can use FU for formula units. And then rocking out that across, it says 1 mole over Avogadro's number. So I'm going to put 1 mole on top. That's of sodium chloride. And then on the bottom, I'm going to put Avogadro's number, 6.02 times 10 to the 23rd. Particles. Remember, the particles specifically are formula units. So I'm going to put formula units of sodium chloride. Now that I have that, let me double check that my work balances out here and cancels out. Yep, formula units of sodium chloride and top and bottom cancel. I'm left with moles of sodium chloride on the bottom. So when I do that, I've got 500 times 1 divided by 6.02 times 10 to the 23rd. Again, make sure you can put that 6.02 times 10 to the 23rd in your calculator properly. That's important. Otherwise, you're going to get the wrong answer. Now, let me make some room to write this. My equal sign was a little too close. So I end up getting, when I put that in my calculator, 8.31 times 10 to the negative 22nd moles of NaCl. That is a very small number. Remember, if it's to the 22nd power, you're going to move to the left 22 decimal places, okay? That's a really small number, 0.00000. So it's 0.0 with 21 zeros, 831. That is extremely small. But in the end, that's how many moles you have. A very small amount when you only have 500 little tiny formula units of salt, sodium chloride. All right, that was a bit for the one-step problems. Let's just answer these quick ones, 16 through the rest of them. Covered up all that work. Let's focus on 16. How many atoms are there in a mole? All right, if you have 1 mole, that means you have 6.02 times 10 to the 23rd pieces or atoms in a mole. How many molecules are in a mole? Same thing. If you have a mole of molecules, you have 6.02 times 10 to the 23rd molecules. How many donuts are in a mole? If you have a mole of donuts, remember it's a word that represents a number, so you have 6.02 times 10 to the 23rd donuts. How many candy bars are in a mole? Yep, you guessed it. If you have a mole of candy bars, you have 6.02 times 10 to the 23rd candy bars. So a mole is a word that represents a number, and as you can see, it also allows you to convert to mass, volume if it's a gas at standard temperature and pressure, and also particles, meaning molecules, formula units, or atoms. All right, science fam, nice job hanging in there. We are getting closer and closer to being able to use this to help predict some really valuable information. But again, this is Avogadro's number related to the mole. Let's keep cracking away and learning together. Take care.